Hi everyone, so I'm Louis-Philippe Gauthier. I'm Director of Platform Engineering at AdGear. Today I'm going to be kind of unveiling my new HTTP client I've been working on for the past 3 months about, on and off. So let's start. Buoy's, the name of the client is Buoy. So the raison d'être is basically why I built this. A little bit of a story. So in 2011, when we started building our platform using Erlang, the first client we used was called Eyebrows, which actually still exists and is still active, which is pretty impressive. I did look at the issues list, and my issue from 2011 about leaking connections is still there. So I don't know if you should use it or not in production, but we'll see later that it actually does fairly well in the benchmarks. Starting 2011, Fred Hébert, who used to work with us at AdGear but decided to leave, actually built something called dihttpc that he presented here a couple years back. Dihttpc was a way to add back pressure so that we don't get overloaded by sending messages to processes. And so in an effort to scale our HTTP client, we forked dihttpc and added a pool mechanism using dihttpc. When Fred left in 2012, or at the end of 2012, I took over his fork. So at this point, it was a fork of a fork of a fork. And I kind of changed to everything to use binaries, and also to not spawn a process on each request. So I introduced something called like a timer killing functionality, pool to receive timeouts. Anyway, it's super complicated. I do not recommend it for anyone. And so this year, finally, we've been kind of hitting some walls because of partners that would go down or be too slow. So because of the functionality, I didn't want to add more to it. I decided to just re-implement a new one. So in 2017, we're going to start using Buoy. Currently, we're not using it yet in production. I have done tests in prod, but just because of lack of time, I haven't had time to deploy it. So just to go back to the problems for dihttpc, one of the biggest problems is that it does not support pipelining. So with the model of dihttpc, dihttpc adds back pressure, like I said, but only allows one request at a time to go to the worker. And because of that, when there's more than one request sent, instead of timing out or waiting, it just returns error busy for now. We'll see later on with benchmarks. I actually found that in really heavy conditions, there's actually like 97% error rates. So like almost no request goes through, which is really not efficient. The other problem was it reconnects on requests. So whenever connection closes and the other server is unreachable or timing out, we just hammer it until we can get a connection. But often we just end up running out of like file descriptors on the other side or causing more issues. And yeah, when we forked it initially, we did not fix the test. So when I forked it again, I did not fix the test. And the test suite is just a mess, and there's no ways to know if the code is actually OK. And basically, it's just hacks on hacks on hacks. So we decided it's time to write our own. So Buoy's architecture. The architecture is really simple. Basically, if you have a process that wants to do an HTTP request, it has to call a module called Buoy pool utils, which will do the translation from the URL to the pool name, which is a Shackle pool. So I'm going to explain after this what Shackle is. If you were here last year, I presented about the framework I've been building over the last 3 years. But let's see in a second. So Shackle framework. So what does it do? If you have an application, you want to talk to an external service, Shackle is probably what you need as a basis to build your client to have some properties. So before we go further, what's a service? So a service in Shackle, it's something that communicates over a socket. This could be UDP, TCP, and recently we added SSL. It can speak either in a text protocol or in a binary protocol, and it can be a synchronous or asynchronous protocol. The goals. So why did I come up with this framework? Basically at AdGear at this point, I think we're up to 7 different clients that we maintain all the time. It's very painful to add an optimization in one and then port it over to the other ones. If you were in the previous talk with the React upgrading to 19, dependencies become really complicated, and it's really painful to open 6 PRs every time to kind of patch the different places. So the first goal was really reusability so that I don't have to reinvent the wheel every time I write a client. The second goal was speed. And by speed, I mean low overhead. So speed of the request itself needs to be as low as possible. The pool cannot add more time. We don't want to be stuck in a queue. And we want it to be as fast as possible, as optimized as possible. Speed is great, but without concurrency, you're very limited. So if you can do 1 request in 1 second and you have 10 cores, then you can do 10 requests per second. But if you can do 10 concurrent requests, now you're up to 100 requests a second. So it's really important to also think about concurrency, which Erlang is great at. So it's an important concern for me to keep it as highly concurrent as possible without adding any locks or any kind of bottlenecks in the code. Finally, safety. So safety is 2 parts. One part is a back pressure mechanism that's implemented in Shackle. So if you're asking 1 million requests a second to your client, you don't want to queue up too many messages in the queue. So there's a mechanism of a backlog that will limit the number of messages you can send, and therefore you'll never end up running out of memory. So that was one of the problems that we actually solved initially 4 years ago with discount, and this is kind of the evolution of it. The other safetiness is the fact that everything is really, there's error cases for anything. It should never crash. I know you've probably heard talks about let it crash. It is a great functionality of Erlang. It makes sense for parts of systems, but if you're doing high-performance Erlang and you're trying to keep your system up and running, often the crash path will be much slower. You'll be logging, you'll be getting a stack trace. You cannot do that 10,000 times a second. So a little overview of Shackle. So last year when I presented, these were basically the features that were supported. So it's multi-protocol, TCP, UDP. There's a very fast pool implementation that uses some tricks that I'll explain later. Supports round robin and random selection of workers. It supports request pipelining, which is very important if you want to have high concurrency. It supports back pressure via backlog, so to protect from out-of-memory errors. And finally, there's a smart reconnect mechanism, so there's exponential backoff, and the connections are maintained by the client. It's not on a request basis. If we look at this diagram, that's basically how it works last year. So you have a process. If it wants to do a request, it's actually going to talk to ETS first. Ask about the pool options. From the pool options, it'll find out what the strategy is, so how to select the worker, the pool size, and the backlog size. From this information, it's going to generate a name for a server, and then call ETS again to check what the backlog size is. If it's below the maximum backlog size, then it will send the request to the worker. So when it does send the request, it's a message sent to a client. These clients, I'll show you a little bit later how it's implemented and how we implemented it in Buoy. These clients are just small servers using proclib so that they can be supervised. And finally, they just send messages via sockets to a service. So that was last year. This year, some features that were added during the year. So now we have managed timeouts. So timeouts used to be just on receive, you'd have a timeout, which kind of made it difficult because if you called a call or a cast, the behavior was different. You had to implement yourself the timeouts, and which meant that you had to clean up the backlog yourself. You had to empty the queues yourself. It was complicated and error-prone. So this year now we use Erlang send after for every request. And because of that, everything gets cleaned out properly, and all the calls are kind of symmetric in their implementation. We also added SSL support. Obviously for HTTPS, it's very useful. Another feature is that we added error in the handle data callback. I'll talk about it a little bit later. This was also for Buoy, and we did a lot of optimization. One of them is using GrandErl. GrandErl is a NIF to do random number generation, but very fast. Not be used for crypto, please. We added a cache. So instead of doing, previously we would do a call to ETS to figure out the pool options. Now we don't do that. We use a little trick that I'll explain later, but basically we compile the ETS table into a module that we read at runtime, and instead of doing a call and having synchronization between processes, now it's a module, it's lock-free, and there's a much lower overhead. And the other kind of major optimization, wherever we had a state that was a record that would get mutated, we try to split these records as much as possible so that as little as possible there'd be any mutation. So set element 3 call, if you write Erlang, you know that that's the function call that's called when you modify a tuple. And this is costly because it occurs a lot of copying. So if you can remove as many mutation of tuples, you gain speed because of less GC, less memory pressure. Another change, if you look at this graph here, it used to be proclib. It's still using proclib, but I added a layer called metal. Metal is a little server, I guess, behavior I implemented that I noticed I was implementing in everything I've been building recently, so I pulled it out. It's just a simple server behavior that is close to the metal. So today, when you're doing an actual call with Shackle, this would be an example for Buoy. So you have your pool name. So this is what gets generated by Buoy pool utils that we'll see later, but this would be the pool name. Beside you have the message, the request you're sending to the server. The next thing it does is it tries to find a server to send this to. So it will call options, it will call Shackle pool util options to get the pool options. And like I said, this is now a module. If we did the same stack trace last year, it would have been an ETS call. Now, from these pool options, we know that the pool strategy is random. The number of workers, the pool size is 16, and this is the name of the pool. So we call random 16, which is backed by GrandErl now, and we generate the server name, which is just an atom. From this, so we get this name, we call backlog check with the maximum backlog size, and we just do an update counter to an ETS table to check what the backlog size is. If you're wondering what these options are, it's a little trick you can do to know if your counter is going to go over without going over. So you can do two operations at the same time, adding a limit and setting what the limit, if is attained, where it should go back. So doing this call, if it increments, let's say you're at 0, they'd both be at 1 and 1. But let's say you're at 1024, one would increase and the other one would stay the same. So other features that are upcoming, because my coworkers decide to keep using new protocols all the time, So SCTP network protocol is coming because one of our services is going to use SCTP now. There's more optimizations coming. I really need to redo the test suite. It does an okay job at covering, but it could be much cleaner, much more complete, and better documentation. I've been looking like a bunch of new frameworks coming out for Rust and stuff, and they have marketing materials and documentation with fancy images. Right now I just have like a GitHub README, so I need to step up my, my documentation game. Just a little note on the usage. So we use it really extensively at AdGear. That was really early this morning, so the requests are not too high. But so at 4 a.m., I guess, it was 2.5 million requests per second. Peak, I think we can reach 5.5 million requests a second with Shackle. We have a bunch of different clients. You can see, or maybe you can see, so for some of the requests, it's even in microseconds. So speaking to our IP list service, a request takes an average, or that's the 95th percentile actually, 211 microseconds. So I do spend a lot of time optimizing this code. Performance is really important for me, so, and especially when you're doing that many requests per second. So that's it for the Shackle intro. Now I'm going to talk about Buoy, how it's implemented using Shackle. So to implement a Shackle client, you have to implement a behavior that's defined like this. So the first thing is there's an init state. The init state will initiate basically the state of the client. So if you need a record to keep the state, or if you need to do any kind of operations, this will be the first thing. Then there's a setup phase. So the setup phase will receive the socket, and then that's when you can set up stuff on the connection. So if you're speaking to Cassandra, for instance, it could be that you set the key space. So a default key space for the whole pool would be done in this space. After that, the two really important ones are handle requests, handle data. So handle requests is the callback that will receive the actual requests from Shackle call or Shackle cast. So that's the one that's going to serialize into the protocol that the service expects. When the service receives the request, sends back the response goes to handle data. So handle data will be decoding the response and sending in the information back to the callee. Finally, there's terminate. So whenever the connection closes, it calls terminate so you can clean up the state you created in it. So for Buoy, it's fairly simple. So init, just create a new state. In the state, what we have is a buffer. So it's just a binary buffer because often TCP, well, HTTP requests will span multiple TCP packets. So we need to buffer in case it doesn't fit in one. And then we keep two counters, so requests in and requests out. And these are used to match the request with the response for the callee. So if your protocol allows you to send a request ID with it, and when you receive it back, you can do that association easily. But for HTTP, you cannot send any data and receive it back. So since it's supposed to be kind of linear, so you're supposed to receive the response in order. What we do is when we send a request, we increment the counter, requests out, and when we receive a request, we increment requests in, and this is how we know the right ID for each request. This only works because the ordering is supposed to be maintained. If the order is not maintained, then this doesn't work, and you need to send a request ID in the protocol. Handle request. So handle request, like I said, receives a term which will be encoded into the request you have to send to the server. So in this case, I do all the encoding of the requests outside of the server. so that the server can stay as lean as possible and only process requests sending as fast as possible on the socket. The only thing I do is I generate a request ID, and I just keep it under 32-bit for no reason. Because I copied that from another client, I think. But it would work without this and just sending the other ID. Actually, this is a little opportunity to optimize the code. And then what we do is you send OK, the request ID, the request, and then you can update your state. And once this is done, so the request ID will be queued up, and then the request ID will be queued up and the state updated. And you'll see the next is handle data. So handle data will receive a HTTP request that it needs to be decoded. So I'll take the buffer, keep the buffer, add the data to it, or append the data to it, and then call responses. And from there, this is basically all of the code in the client. Responses will just call Buoy protocol response to decode the response, and either it gets a response right away or it does not have enough data, so we need to buffer for the next time we get a packet. If for some reason the request is invalid, we'll return error reason state, which will actually shut down the request right away and send socket close to all the caller that are queued currently on that worker. So previously, that's what I was talking about. This is the new state that you can call on that callback for handle data that was added for Buoy, so that if the protocol, if for some reason you're talking to the HTTP server that doesn't respect the specs or is corrupted through a proxy or something, it doesn't bork all the following requests. Buoy protocol. So encoding a request, I really kind of went basic here. What we do is we calculate what the content length is, which is the size of the body. The body is an IO list because IO lists are great for high performance because you don't need to create new binaries. So basically, whenever you have a bunch of binaries that you need to glue together instead of appending them together, you can use an IO list and generate it without incurring the cost of creating a new binary.
Why did you do that earlier, though? When you accumulated the buffer, you did an append.
Right, because of the parsing, we'll see the parsing code after, but the parsing works on binaries, unfortunately. You can't do binary matching on IO lists yet.
Could you just accumulate that and then do a IO list to binary at that moment?
So it is at that moment.
Well, you're accumulating the binary.
Right, but
It's
it's like one step before. After that, what we do, so we add content length to the list of headers. You'll notice here we hard code connection keep alive. This is one thing that's really important. Buoy is made as an HTTP client for like high performance between servers. If you're not doing keep alive, there's no point of using this. You're wasting resource opening connections all the time. It's not going to work great. Your logs are going to be full of errors, trying to reconnecting all the time. So this is one of the things I decided when building this. Keep alive only. It supports only HTTP 1.1. Don't even try with 1.0. It will tell you it's not supported. And then it formats the headers. Again, this is just kind of a map over the headers, and it builds an IO list that then is put in this big IO list. So it's really, really simple, and we don't create any binaries at all during this. The decoding of the response. So the HTTP parser I wrote is very small. It's about 150 lines tops, even. I think it's a little bit less than that. I evaluated a lot of parsers that exist already. Most of the newer ones go with the streaming approach. There is value to a streaming, but the problem with streaming usually is that you have to maintain a state, and maintaining a state usually means that you have to mutate something. So I did benchmarks against Acme's parser, that's basically cowlib's parser, with some modification. And really, like, you could see, well, mine is 10 times faster for the same requests. And basically, it's just because of mutating states and always calling the same functions over and over, because you need to keep a state saying, OK, like, one header was parsed, another header was parsed, another. And you're just looping always until it's done. Instead of doing kind of one big function, I split mine. It is a streaming-ish. I do the headers and then the body, but I don't do 10 passive headers and continue that way to minimize function call, minimize sub-binary creation, and minimize set element calls. Another thing I do, which is to minimize sub-binary creation, is use binary split. And because of speed, binary split ends up being faster than actually just binary matching on new lines and iterating until you find a new line. I did some benchmark just to make sure it was actually faster before this talk this morning, because somewhere else on the internet I read that it was slower. So I didn't want to say stuff that wasn't true. So I did benchmark these two, a simple kind of binary match that we iterate until we find /r/n, and then return. And the same kind of function, just using binary split. Doing it really a fast kind of micro benchmark using one of my libraries I'll talk later. The split takes, on average, 16.3 microseconds. Yeah, the split with hype. Yeah, this is wrong. Should be, OK, so split 2 should be 16. So the fastest is binary split. Split with hype is a little bit slower, and split is much slower. I'll fix these numbers after, but I'll talk also about timing HDR. It's a little library I wrote to do micro benchmarks. And this is basically the graph that it outputs if you do using the HDR histograms. You'll see that split 2 is a little bit faster, split hype is close by, and then split is slower, at least over like the 90th percentile. So to continue with the protocol, it implements a subset of the RFC 2616. Some of the unsupported features, some of them I do not plan on doing ever, so arbitrary number of new lines and headers. So if you're using some weird web server that just adds new line and headers at the end, it won't work. I've tested with most traditional web server like Apache, Nginx, whatever, it all works. But if you're building your own and you're doing some weird stuff, it probably won't parse. Capitalization of headers, so if we're looking for content length, it'll be all just the first letter will capitalize or none of the letters capitalize. If you're doing random, it won't work. There's no protections against malicious servers. This is meant to be server-to-server, speaking to a partner or someone you trust. If they send you, I don't know, a content length of 6 billion, then you're going to read 6 billion and you're going to run out of memory. And finally, chunk encoding for now is not supported. This is kind of because Shackle can't support it currently. If there's enough demand for it, I'll implement it. So one of the cool optimization that has been done in Shackle and also in Buoy is something and this is called Buoy compiler, but basically for states that are only read-only that usually I would store in ETS, I move them out of ETS and I use URL syntax to actually generate AST on the fly and compile them. there's some nice tricks that you can do. So this is kind of the code example. So my pools are in my ETS table pool. I do tab to list on that. From there, I send it to pool utils form, which will generate the AST, and I send it to compile and load forms, which will load the new module. And this has been working great in production for about 1.5 years now, so it's fairly safe. I haven't tested on like super old versions of Erlang. I know it wasn't, I think pre-16 module were not loaded asynchronously, so maybe that would be problematic, but in the latest Erlangs it should be okay. I use Erl syntax to generate the AST. It's low verbose, but works fine. If you're using, if you don't care about backwards compatibility, I think there's xmerl now, or merl, to do this, which is a macro library on top of Erl syntax. You can see here, this is basically the module definition. So it's building a module called pool utils. This is the export list, so it's going to export one method called name with 3 arguments. And this is going to be the function definition itself. And then I'm just going to generate the name clauses from the pools, which is what comes from ETS. And the compile and load forms is basically I compile the forms from that AST. It generates a module and a binary. Well, the module is just the name of the module and a binary. We purge the all module, create the module name, because we need a module name to do load binary for some reason. And then we load it dynamically at runtime. Buoy's performance. So, like I said, performance for me is really important. One of the tools I have is I have a make profile target, so I can run whenever I do a change. I type make profile, and then I can look at what change and see if there's an effect. For this profile target, I use fprofx, which is a fork of fprof that adds suspend and GC time. And from this output, I use K or Q cache grind to visualize the output. So this is kind of what it looks like for my make target. I'll just call, so I have a module to do the actual profile call. I run it. It outputs a file fprof analysis. I send it to Erl grindx, which is a utility that comes with fprofx to transform the output in something readable by K cache grind or Q cache grind. And what you get is this nice little graphical output. So I can figure out which function was called how many times, the included time of all the things on the stack below, and how much time was spent on itself. It's also great for visualization. You can see really visually where the time is spent. Also gives you these nice little graphs where you can see all the callies and how it functions. So earlier I showed you guys the Shackle call. So Shackle call calls Shackle pool server calls server index, backlog check, pool options, and the random call. So you kind of see where the time is spent, and it's great. This is the same output for the server. So I said we're using metal now. So there's metal, the metal loop, which is implemented by Shackle TCP server message. And then there's the 3 branches of where work is actually done. So the TCP send, so this is sending data, this is receiving data, and this is processing response. Another tool we have, we use at AdGear is extrospect-beam. It's been written by Julian Squires at AdGear. He presented it at EUC last year. A really cool tool that works, fortunately or unfortunately, only on Linux. Uses perf events on Linux to sample what's happening in the VM. So it's pretty easy to use. You can use, there's a utility called Erlang write perf map to write the perf map to map the functions in the VM to perf events. And then all you have to do is do perf top in the PID, and you can see in the VM itself what's happening, but also in your beam. So there should be so you can see Shackle call, but you can also see a lot of allocation and scheduler getting data and stuff that normally you would not have any visibility on. This tool also comes with something to just sample Erlang. So with this tool, you can do Erlang sample, only Erlang, and pass a PID. And now you only get the Erlang functions. You can see, like I said, I use binary split heavily. In this, it looks like that would be kind of my next optimization would be either to get rid of binary split. I'm guessing I could write like a simpler NIF to do this work, although I do not want to introduce more NIFs in our code, so we might just have to live with it. So the fun part, benchmarks. I built a suite called dihttpc bench. It used this project called timing, which is on my GitHub. I added a new module in there called timing HDR, which uses HDR histograms that was initially written by Gauthier from Azul Systems. That was written in Java. There's a C port that was written a couple years ago. And I think a year or two ago, there was a NIF written to wrap that C code. This is actually one of the only ways I found to do kind of scientific histogram. It's really hard to get it right. I trust that the science or like the stats behind it are right. And so far, I haven't found anything that proved it wrong. This suite is on GitHub. If you have an HP client or you think you can improve the results of another client, feel free to send a pull request. I really want it to be kind of as representative as possible for HTTP clients. The clients I benchmarked this year, so dihttpc2, Acne 162, HTTPC, which is the Erlang client, Eyebrows, Catipo, and Buoy. The bench servers, so I use two of our prod servers that are not in rotation yet. So there are 48 Xeon cores, 256 gigs of RAM SSDs, and the latency between the servers under 0.1 ms. And I realized this morning it was running Erlang 18.3 and not 19. I'll rerun the benchmarks to see if it makes a difference, but hopefully it doesn't. What HTTPC does is it'll do a number of iteration, and it'll do for a number of concurrency, so number of process doing requests or doing an operations for those iterations. And then there's also a pool size, so how many connections should be open, how many workers in the client should be there. So if we look at DLHTPC, we start by a pool size of 8, concurrency 32. I can get 16,950 requests a second, and the error rate is 91.3%. So this is awful. Like 91% of the requests do not get a reply. You'll get just error busy. This is how this count was implemented. It's unfortunate, but it keeps the latency really low for the few requests that make it. Which, I don't know, I guess it's good, but kind of bad. You'll see that as the pool size increase, well, you'll see as the concurrency increases and the pool size stay the same, the error rate increases because there's more and more requests asked, but the number of workers does not increase. The more you increase the pool size, you'll see the error rate dropping lower and lower, but there's always a threshold where it can't handle as many. And although increasing the pool size seems to be helping, eventually there'll be a trade-off where having 1 million workers is not going to, it's not going to help out. Apparently there's not much time left, so I'm going to go a little bit faster. For Acne, I think the problem is there's no pipelining, so the results are not super exciting. HTTPC, pretty brutal. Eyebrows does okay for a fairly old client. I think the max it can do is 55 or 58,000 requests a second, but increasing the pool size does not seem to help. It actually decreases. Catipo is, so that one is actually a port driver wrapping libcurl. It does okay with a small pool size. In the other one, pool size also equaled connections, number of connections. In this one, I cannot control the connections. I think there's a patch that was merged that I'll be able to do it, but until then, the benchmark is a bit flawed for this one. But if you have a pool size of 8, you can reach up to 96,000 requests a second, which is by far the fastest of all the other ones. But as you increase, there's no increase, it actually decreases. So it's really, I think you hit a bottleneck serializing between the C port and the VM. Finally, Buoy. So the exciting part, everyone's waiting. So for pool size of 8, you'll see it gets overloaded at maybe like 512. So it decreases. The more you add, though, the more it augments. You can see with 128, the pool size, concurrency of 248, requests per second is 604 thousands a second, which you can see with this nice, pretty graph, increasing, the second number is the pool size. So increasing the pool size usually will make the latency better because there's more, there's less requests in the queues, and therefore they can be answers quicker. The final results, so Buoy, the max in this benchmark was 605,000 a second, which is 6.3 times faster than Catipo, 8.6 times faster than dihttpc, 10.2 times faster than Eyebrows, 18 times faster, and 43 times faster than HTPC, which I think is pretty cool to get these results. It's rare that you get 10x on anything. Some tips and tricks, pattern match everything. It's really one of the most efficient ways of parsing or doing anything. So as much as possible, usually I try to pattern match using IOList. I said it before. Keep your server loops lean. So if you have a loop that's receiving messages, specialize your loops. Don't do one big loop that will receive all the messages. The specialization will be more efficient because it does not have to match messages that it doesn't need to see. Use ETS for shared state. Compile magical modules for read-only states instead of ETS. Cool trick I actually learned working on this is there's been op-info compile option that will tell you if a sub-binary will be optimized. Because if you're creating sub-binaries, the compiler can be smart enough sometimes to optimize and not create the sub-binary. It will tell you if it's able or not to do it. So if you're creating sub-binaries, try with this option. You'll see maybe the compiler can't optimize it, and you might be able to change your code to optimize more. Measure everything. Intuition is great, but often it's wrong. It's much easier to just run a small benchmark and figure out what the reality is. Some links. I have a lot of projects on my GitHub. Julian also has some interesting stuff. I'll be publishing the slides on my Twitter after, so if you have questions or you want to find these projects, feel free to send me a message. And thank you.